Hi everybody. So yesterday I started working with the new feature here, which is broadcasting mode in client-side caching. However, the events were faster than expected. So yesterday, Redis developer asked to review the old idea of the client-side caching, which is based on hashing the key name in order to obtain from the key a caching slot. We explored, thanks to his input, the idea of using directly the key and what is the trade-off. Probably it is a bit less efficient because instead of having an array of slots pointing to radix trees of client IDs, we will have a radix tree with all the keys pointing to a radix tree of client IDs. And hashing and the linear access to the array is faster than accessing the radix tree here. And also this will use more memory, and there are a few drawbacks. However, the point was that anyway, when we reach the maximum allowed number of items, we are going to expire in the client side a lot of keys, because an invalidation message about a caching slot will collide with multiple keys that the client is caching. And also the interface transferring just key names is much simpler to implement from the point of view of the user. So yeah, it's probably a good idea to switch to such design. And given that the implementation should not be so hard, I'm going to implement this in a new branch so that we can evaluate it, not just theoretically, but also to have a feel about it works, the memory usage to cache the same number of information, and so forth. And we will continue later with the broadcasting part. Also, the broadcast was already about sending the key instead of the caching value. So this will kind of unify the two implementations. If the hashing approach could have so strong improvements over the sending key approach, I would go for it, not caring about the complexity in the client-side implementation. But it looks like the advantage is small, and in certain ways it is also a problem, because we have to allocate a table beforehand and stuff like that. So all in all, it looks like a good compromise. Here we will have to rework a lot of comments, because everything assumes this. So we will write instead that the tracking table is constituted by a radix tree pointing of keys pointing each pointing to a radix tree tracking clients. So the tracking table is constituted by a radix tree of keys, each pointing to a radix tree of client IDs used to track the clients that may have certain keys in their local client-side cache. Okay, then it no longer makes sense to talk about lazy allocation because it's obvious, it's too dynamic data structure. So keys are grouped, blah, 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 blah. No need. When a client enables tracking with client tracking on, each key served by the client is remembered. So the client is remembered in the table, mapping the keys to the client IDs. Later, when a key is in a given, when a key is modified, all the clients that may have a local copy of such key will receive an invalidation message. There is no distinction of database number. A single table is used. Actually, this is a problem now. We cannot do that anymore because previously we could not care about the database number, since we could say like they will collide, and given that anyway we are compressing our namespace to a single number of slots, who cares? Instead, in that case, we want actually to provide the database number, and we will find a suitable scheme. And I think it's not a good idea at all to just have multiple radix trees for each database. We need to find a different encoding where probably we prefix some 4 bytes database ID and then the key name or something like that. Yeah. Clients will normally take frequently requested objects in memory, removing them when invalidation is a strategy is to just cache objects in the dictionary, or just timestamp. When invalidation messages are received, the clients may store in a different table the timestamp of the invalidation of given keys, such a given key. Okay. Later, when accessing objects, the eviction of stale objects may be performed in a lazy way by checking if the cached object timestamp is older than the invalidation timestamp. Well, with the key, this is probably no longer needed, because at this point I think we can just receive the key name and directly invalidate the key name immediately by removing it from the dictionary of hashed things, the dictionary of cached objects. Yeah, let's reason a bit about this. So we need to draw. So basically, this is a big simplification, but we need to be sure that we are not missing anything. So this is the client, and the client has inside an hash table. So we request a key, hey, this is the server, and we get back the value, foo. So we associate e equal foo here. When we receive from a different channel here an invalidation message, the most obvious thing to do is just to invalidate it. There is just one race condition here. Yeah, imagine that I ask for A here. Before I receive back foo, I get a new command here from another client touching the key A again. So I receive the invalidation message because maybe this link is faster, and then I get foo. So I invalidate this before, and then I get foo and I delete this. So actually the client must use a more complicated protocol, which is when A is requested, we set A to waiting, a special object saying we are waiting for the value. Then if foo arrives and we have this set to waiting, we can actually set foo instead of waiting. However, if the invalidation message arrived before and evicted A, and when we receive foo here, and we see that we have no A at all in our table, we don't set foo because it's already expired. So this is a protocol in order to avoid race conditions from that point of view. And well, the clients also will have probably to associate a TTL with each object, both for safety, so that if this link is too idle, from time to time will expire if there are problems. Values will not be still forever. And also because we could want to model TTLs. So instead of a get, we do get plus TTL, and when we set this TTL in order to match more or less the server TTL. Okay, this is not needed. Okay, at this point the tracking table becomes just racks. Used slots we don't need anymore because it's like just rack sides. However, what would be cool to have it's tracking table total items. Okay. Tracking channel name, we still need it. Okay, remove the tracking state from client C. This is like that. Enable tracking. If tracking table is null, tracking table is racks new. This function is called after the execution of a read-only command. In the case of client, it says, okay, remember keys. Okay, we just extract the keys of a command, and okay, SDS key, we no longer need to perform the hashing. But instead we do this. Okay. And if such key doesn't exist right now, we just create it doing if IDs racks not found, IDs while racks and we set it. And okay, here we want to use the key name. Okay, here we have the problem of the database ID. Yeah, that's a non-nice problem. Okay, what we can do here in order to simplify the implementation is to do what the old implementation did, which is to collide different keys in different databases in the same space. So if you are caching two keys with the same name in two different databases, we send you the invalidation message whatever one or the other was invalidated. This is reasonable and will save us a lot of CPU time, because otherwise we have to compose the key, and it's expensive and probably it's not worth it. So we insert here this stuff here with the key name, IDs. Okay. And here it's a good idea to add an assertion. Okay. And now we can insert this ID here. And if we actually inserted this element, we can increment the number of total items that we have in the wall tracking table. Okay. Okay, this is not worth any commenting because it's obvious what's happening here. This sends tracking message. However, it's no longer an hash, but it's something like I imagine something like that. So add reply bulk C buffer C no, this is a different story. This is the tracking ready broken message. It's here that we want to change the thing. So we no longer have the hash, but we here add reply bulk C buffer C key name keylen. Okay. Create string object. Hash. Here there is a bit too much copying going happening because anyway this stuff here will just copy. So maybe we need add reply bubsub message buffers, which will just take char and length. But we can fix this later. For now, it's correct even if it's slower. So or we could create here like a static string object. We had something like, yeah, we have this. We have this. This should work correctly, I think. And okay, let's see actually what this stuff here is doing. Oh, I changed my keyboard for error to Italian. Yeah, this is just a trick. Perfect. This is what we need. Because anyway, the way this will be used should be fine, which is add reply bubsub message. Add reply bulk message, and actually right now it's perfectly fine because as you can see, we just copy to the buffer here or here. Anyway, however, this is not very future proof, so it's not really great from that point of view. What we can do instead, yeah, we should modify this function here probably, but add reply pub message. Or we could leave a comment here. And what we can do is this. Okay, in this way we can verify that the implementation is still doing what it should be doing. Okay, well, we need to merge these two functions, invalidate slot and invalidate key. So we call this tracking validate key. Remove the comment, get the comment from here. This check is redundant, so we don't need this anymore. Yeah, we take the STS key and this is all useless, I guess. Okay, we take the key object, we need the iterator, and okay, Rax start. If tracking table equal null, return. Okay. Otherwise, we have our IDs. Seek and send tracking message. Here. If the client exists. We stop here, and what we do before freeing the IDs and removing with Rax, before forgetting, we do this tracking table total items minus equal Rax size IDs. So we take the count updated. Rax remove tracking table. It's the same of this one here. We don't want the old value. Okay. Invalidate keys on flash. This when we use the hash values, we could just use -1 in order to say that the whole key space was flashed. However, now we cannot do it anymore. I guess that a sensible alternative is to send the empty string as a key name, even if yes, it's possible that people could use people could indeed use the empty string as a key name. It's possible, so let's take a few notes about that. Okay. Certain clients. Let's reclaim all the memory used by tracking. So we need to do this in a different way, like racks free with callback tracking table, racks free. Yep. And this drops to 0. No, you know, now it's silly every time to destroy the racks, create the racks. Again, we should do that on initialization and do it, and that's it. Anyway, it's radix tree is a few bytes. It's no longer a large table. Okay. Okay. Tracking forces Redis to remember information about which client may have keys about certain caching slots. May have certain keys in workloads where there are a lot of reads, but keys are, if I remember, server side could be a lot. Okay. Okay, here it's in percentage, and we need to change that to be just a number. So this is not needed at all. We could decide if to make this limit about the number of keys or about the number of objects tracked, which is our tracking table total of items. Probably it's very hard to reason about the number of IDs stored globally, so the number of keys is more high level, even if not exactly accurate from the point of view of the total memory consumed. So we do something like that. Okay, for now, let's use just this as the number of keys. Tracking limit used slots. Okay. 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 Here we try to limit the effort that we are doing here. In this case, our work was very simple. This time we have to do something a bit more complex, something like that. Rax iterator start ri when I use steps, but if I use 0 steps, if 0 it's okay, calculated based on the logarithm. Zero. So here I'm pointing to some node. Okay. Actually, I should do this rack start thing. Okay. Let's do this here. And let's do this here. And there is a return statement here. So here we seek, and we do a random walk to select a random element. And once we have that, we get the IDs. Which is, oh no, I think I can just use Okay, effort should be greater than 0 and rack size tracking table greater than 0. So I'm sure here that there is at least one element, and when I do the random walk, which is int greater than 0 if the tree is empty, okay, or out of memory. So well, actually we can do just while effort is greater than 0. Okay, oh, it was in the original code. Okay. I think we can simplify this code here. So we do the rack start here. The effort proportional to the number of times we enter this function, and found that we are still over the limit. Okay. So we start to be more and more and more aggressive. So if effort is positive, do. Okay, because here we could find empty indexes. Okay, this is the reason. Jump again random in order to create big goals in the table. Okay, we have to invalidate a few keys to reach the limit again. The effort we do here is proportional to the number of times we enter this function, and found that we are still over the limit. Let's start. Okay. Okay, in order to let's start the random walk always from the root node here. It's probably better. So we just remove one other basic random walk. While effort is greater than 0, we don't need this jumping stuff. So we do effort minus minus Redis seek rack seek the start and perform a random walk. Could be also interesting to continue the random walk from where we are. That could be a potential possibility, and that then we will do a different seek. Okay, this is probably more conservative. Okay, if we go in a node which is kind of self-referencing with other nodes, otherwise we never skip easily again. Okay, so racks IDs equal racks find. No, we have directly the RI data, and yes, what we do here is and we free it, and we remove this from the tracking table. Should be something like that. We'll check later. Yeah, we remove it, and if we were able to reach a situation where we are under again the limit, max slots, we don't have it anymore, so max fill, okay, we call this for now. We will do some refactoring later because these names are wrong. If flag size is less than max keys, okay, we are fine. But okay, time counter. Okay, if we reach this point, okay. This should be like instead get used get tracking get total items. Okay. Yeah, should be something like that. It will never compile, of course, but at least we got a general idea about what we should do. And okay, we removed more code than when we added. So let's try what happens. Just bugs after bugs. Okay, many errors. X. Okay. Here we got the key, and then we do X. Okay. Key name. What? Okay. it wanted void. Okay. This doesn't work. Okay. Yeah, we need in info also to substitute this. Okay, so basically now it's compiling. We have to check if it crashes, if it's working, and whatever in the next session. But in general, we kinda tried to convert from the hashing based implementation to the keys based implementation. The conversion took 1 hour. Would be like 30 minutes just coding without talking, but talking helps to reason a bit more about what one is doing and the potential compromises. Thanks for watching. See you the next time. No, the commit actually.